Hello, my name is Miguel Torres. I am part of Ozbay's class for Fluid Mechanics on summer of 2025. I will be doing part 3 of the simulation of a cylinder. This time we'll be doing the turbulence model. Now, the mesh for the first mesh we did worked well for inviscous and laminar. However, for the turbulence model, since I'm going to use K omega, the mesh will have to be a little bit different to get a y plus under 1. Your y plus for slow speed, a low Mach, not over a Mach or anything like that, you will want a y plus under 1, and so the mesh will have to be a little bit different for the boundary layer. So we're going to start her up. Alright, finally, it opened. Sounds. Alright, it opened. Insert, we'll be doing a sizing on cylinder here. Number of divisions, 250. Hard, it's good. Insert. Method, we're doing all triangles here. And then in here we'll be doing inflation. Here, and this is where it gets a little different. I'll be doing total thickness 100, 1.1, no, 1.1, maximum thickness of 1. And then here's also where it gets a little different. Element size would be 0.05. Now we mesh. All right, this is the mesh. Looks good, very fine. And yeah, now we close it and go on to simulation. Okay, we'll leave as K omega. This is what I usually use in Formula SAE under, low speed, um, incompressible flows. So it worked pretty well for me. I'm just gonna stick with it. So there you go. Materials, leave as the default air and make sure it's fluid. It is good. Um, Inlet, the calculated velocity for a Reynolds number of 750,000 is, well, 10.955. I already kind of done a simulation here and kind of made sure everything works out. So there you go. It already kind of saved my parameters. Uh, all this is fine. Make sure it's all good. Reference values, inlet, good. Then you have your, now you have your coefficient of drag that you got to put in and residuals. This we've done in the previous two videos, so I'm not going to show you how to do it. It's the same way. Um, Initialization and initialize. Yep, looks good. Converge. Now we iterate. Run a simulation. Okay. I think I'm ready to say that it is converged. I'm gonna try stop. Wait, it's gonna go lower. Okay. Yeah, no. I'm gonna stop the simulation now. It is a turbulence simulation, so you may not get the target criteria you want. But I'd say I'm pretty fine with this. So I am going to do it a minute. There you go. I'm gonna stop it right now, just to save on time. So looks good. Now, once we finish, I would like to check our mesh. To do so, we could go here, contours, new, and then wall y plus. This is a parameter that could help you determine if your mesh is good. This is for k omega, especially I believe k epsilon could help out too. I'm not sure. Don't quote me on that. But I do know in k omega you have to check your wall y plus. This essentially has to do with your boundary layer, and it has to be under 1. In this case, it is. The max value is 0.2. It's under 1. So I can reasonably say that the mesh is good and that the simulation would be fairly accurate. So there you go. And if you're curious on drag coefficient, we could just run it real quick. There you go, 0.45. That's a reasonable number. Looks good. And then in plots, create a new plot. And we're going to do pressure coefficient for the cylinder. And yep, that looks pretty reasonable. There you go. Same thing for velocity over surface. Oh, velocity, cylinder. And a 0 because it's viscous, of course, it's to be expected. And then here we could do, what was it? Velocity contour. There you go. Looks reasonable, looks good. There you go, you can see the wake. I'll do velocity stream function. Yep, looks reasonable as well. Then pressure. Yep, looks good. And yeah, that is it for project 3 for all turbulence, laminar, and in viscous simulations. This is part 3. So yeah, thank you for watching.